Is that okay?
Yep.
So I can draw my lines in there.
Okay.
Yeah?
Yeah, I think it's all looking good.
Okay. Wow.
The channel.
That was like spot on, right?
Very good. That works. Now stop sharing for a second because I need to actually.
You need to do your bit.
I need to do my bit of introducing you.
Okay.
Yeah, people are starting this coming in. Okay. And let's see, I go by my timer, which is not yet okay, but now we are on the time. Good. So thank you, everybody. Welcome back to the online SPICE-SPIN+X seminar series, organized here by us in the Spin Phenomena Interdisciplinary Center, and that I led together with Karin Eversosite, who is now a full professor in Duisburg, in not such a place as nice as Mainz, but still nice. Then also organize with Collaborative Research Center SPIN+X, that is led by Martina Schliemann, Burkhard Hillebrands in Kaiserslautern, and Matthias Chloe in Mainz. As you know, this is a Zoom webinar format, so you will be seeing the speaker on the slides that are presented. And please write down your questions on the Q&A, and or put your hand up later after the talk is over, and I will hand out to a speaker that you can speak, and I will probably promote you to the panelists so you can have discussions with the speaker and the Q&A. Please, as you know, we will continue until the end of July, and then we will take a little break during August, come back in September in the seminar series that you've been enjoying. Today's speaker needs very little introduction. Christian Pfleiderer. He's the experimental father of fermions in magnetic systems. He's been now a professor in Munich for quite a while, and did his PhD in Cambridge, and actually his master's in the University of Denver, which I didn't know, but has an extensive list of accolades and prizes. One of them, I think the most important one, decided for this topological physics, is European Physics Prize for condensed matter physics for the discovery of fermions in manganese silicon, and has been a leader in the field, particularly helping all of us getting money through leading this expert program on fermionics, and we thank him for that contribution. So I'll stop sharing now, and I will ask you to please go ahead and share your screen and start your talk whenever you like.
Okay. So I have to apologize. I'm not multitasking capable. I had to push buttons first, and then I can start.
That's only Karen that can do it.
Okay, so first of all, I would like to thank Jairo for being so persistent in asking to give a talk in series. It turns out that when the invitation at the beginning of the semester, I had my lectures on Wednesday afternoons, and even though the semester will finish this week, actually I have no lecture this afternoon because I managed to go a little faster and save some time. Okay, so then I guess the second thing to say, and this is, I'm going to be apologizing all the way through this talk, because this is a talk about a topic that I'm not deeply familiar with, and it's the first time I'm talking about this material. And in fact, it might be even the first presentation any of my collaborators are doing on these results. Jairo made me aware that this is kind of like a risky title, Topological Protectorates of Fermi Surfaces. It's not supposed to be political in any means. It's supposed to emphasize that we've discovered some features in the electronic structure of materials that carry a topological charge, or that are in a sense topologically non-trivial, and that are pinned to the Fermi surface by design. And we feel that this is something rather important in this entire field of electronic structures, where topological windings have been very important. So Nothing to do with the fermions, right? It's got a lot to do with MNSI because I've been working in MNSI forever, right? But with this entire materials class. I'd like to start out by just like acknowledging my collaborators. And in a way, all of this is really Mark Wilde's work. He's staff scientist in my group. And Nico Huber, he's a PhD student in our group, and Grace Crosser, who's as a postdoc in my group. And then there's a number of other students who contributed. The samples in my group were prepared by Andi Bauer and Georg Benker. And a major part of the things that I'm going to tell you without knowing much about it worked out by Andreas Schnieder and Moritz Hirschmann and Kirill Alpin from the Max Planck Institute in Stuttgart. So they provided all the input on the topological classification of these electronic structures. Okay, so where I want to start is just like with 2 slides in the spirit of a very brief motivation, and it's looking at the literature. It's virtually impossible to do a comprehensive job of covering the topological properties of the electronic structure of materials. There's a huge zoology of topological materials, and I've stolen this slide or these view graphs from a review that recently Claudia Fels and collaborators published in Nature Materials, and there's a ton of other reviews, just 2 of them are listed here, and they basically allude to this wide range of crossing points, topological crossing points in materials. And there's a type of classification for those. And as you know, all of this started with these questions of band inversion, and then topological insulators was the first big hype. And then more recently, there's a huge interest in these Dirac and Weyl semimetals, where you get more complicated crossing points. And then in the past year and a half, there's been a series of publications address the question of new types of fermions. So these were multifold crossings in the electronic structure. And some of the excitement about this work is that basically there is no analogy with particle physics. While these ones here, typically in presentations on this work, you will hear some analogy to the seminal work in particle physics. But here, condensed matter physics, in a way, opens a new frontier. Right? Okay, now there's a lot of excitement about the different types of things we might be able to do with these materials. There's this business of the chiral anomaly or these axion insulators. There are special like non-equilibrium responses one might expect, and so forth. So there's a huge hope for applications in one way or another, new types of spintronics devices and what have you. However, there's a huge problem, right? Because these materials, in a way, don't behave so well, right? And the crossings are typically far away from the Fermi level, and the effects of the crossings are sometimes difficult to make out. So in a way, the ideal, let's call it Weyl metal wish list, right? Or the ideal wish list for these types of metals is that you want to have the Weyl metals, that you have just a few pairs of Weyl points, ideally just a single pair of Weyl points, that you have these crossings very close to the Fermi level, right? Or perhaps even precisely at the Fermi level. They are sufficiently far separated so you really see the effects in the response in the transport properties and what have you. And there are no further topologically trivial bands floating around that might short circuit effects. And so this is in a way has led to like a material type of search, different compounds, and a huge burst of studies. And that's basically part of the motivation of the work that I want to talk about. So the outline of this talk is that I want to cover a little bit of the literature on these topological fermions in transition metal silicides. And these are chiral materials. And as I said, there were a number of very high profile publications in the last year and a half. I will then say a little bit about the methods that we use, notably quantum measurements of quantum oscillations, the Haas-van-Alphen effect, and the Shubnikov-de Haas oscillations, in order to make one particular point that is essential to understand the results that I will present. And then I want to talk about cobalt silicon. And here, in particular, if you look at the Brilliant zone, the small Fermi surface pocket in the corner of the Brilliant zone. And the interest here is that the electrons that are basically on these Fermi surfaces are cutting through the faces of the Brilliant zone. And these faces of the Brilliant zone are so-called topologically nodal planes. And when they basically, the Fermi surfaces are on these nodal planes, they are topological, and that's what we call these topological protectorates. Right? So whenever you have a Fermi surface basically going through the face of the Brilliant zone, there's a topological orbit associated with it. Right? And you don't have to worry too much about basically non-trivial topological bands floating around, because all of them will be topological when you go for the Fermi surface. Yes, so then after this cobalt silicon, which is a non-magnetic material, I want to address work on MNSI. And you can ask the question, where does these nodal planes basically come from? And the nodal planes are the result of non-symmetric symmetry and in combination non-symmetric symmetries. And they require time reversal symmetry to be conserved, right? But if you break time reversal symmetry, you can basically suppress these nodal planes. And that is shown here. So this is the Fermi surface of MNSI. It's much more complicated. And when we apply a magnetic field in a field polarized phase, these nodal planes basically are suppressed in the direction of the field. So on these faces here of the Brilliant zone, they are suppressed. But on the faces basically perpendicular to the applied field, nodal planes survive, and they enforce, whenever Fermi surfaces are crossing these planes, these topological crossings, right? So these are topological protectorates. And now the nice thing we can do here is we can, of course, change the orientation of the field. And when we change the orientation of the field, we can switch on and off these topological protectorates of different parts of the Fermi surface. And then this, we expect, will have consequences for the transport properties. What I will show is basically just now the studies of the Fermi surfaces. We're not so far that we can make like a full conclusion for the transport properties, but I think this is a very important conceptual step. Okay, so I want to start with an introduction or review of topological fermions and transition metal silicides. And as I said, I will be apologizing all the way through this talk again and again. This is the first time I talk about this. The slides have finished last minute, right, as usual, right? So maybe bits missing. I apologize if I don't cite important work because I'm not so familiar with this field of research, right? And my wording is also not so polished and I'm not so experienced. One of the early works, and perhaps the starting point here for these multifold degeneracies in chiral magnets, is work published in 2017. And they were interested in specifically in these compounds that I will be talking about, the cobalt silicon and the manganese silicon, because they, in the crystal structure, they are lacking inversion symmetry, and the result of that is that basically there is a chirality in the crystal structure. So this is non-symmetric, right? And they look into the consequences of this non-symmetric crystal symmetry, right, in the electronic structure. And they found that there are crossing points, different types of crossing points, that can be in different locations, that can be described with different types of approximate, let's say, like Hamiltonians, right? And this is something then which has become known as these multifold degeneracies, or topological fermions, higher order topological fermions. So it goes beyond these simple Weil and Dirac fermions. So the spin-free halves fermions, or these double Weil fermions, where you have these more complex crossings. One of the issues here is really how important is spin-over coupling. The early work here basically already took spin-orbit coupling into account, while some of the experimental work was the interpretations basically argued spin-orbit coupling is so weak that they can be ignored. But we think that there's a huge difference. So here's a picture where of the, I should say, I think this is basically the calculation of the band structure now for this compound cobalt silicon. Right, it's a cubic compound. It's the band structure. Right, and you can find these crossing points here at the zone center, and then at the sides of the zone, at the R point and the M point. Right, there are also these types of crossing points. There's one thing that's very interesting, which is not being explicitly discussed in these papers. You can already see the effects of these nodal planes in these band structures. So this is a band sticking, which is enforced by this non-symmetric symmetry. And if you look a little closer, right, so these are zoom-ins, you can see that there are all sorts of like crossing points floating around. And this, close to these crossing points, you expect these types of multiple fermion excitations. On the right side, I'm showing this just to already make you aware that there are lots of crossing points in these structures. And of course, you can ask how basically do these different topological charges in the end of the day all add up, because it's one of the important aspects. Basically, they have to sum to zero. Right? So at the end of the day, you have to do like a sum rule. You have to check that everything goes to zero. Okay, now this is from the same paper. These are electronic structure calculations, a theory paper doing different types of cuts through the electronic structure. They predicted that there would be these different types of like neat-looking, very fancy-looking Fermi arcs, right? And that this way, if you do, for instance, photoemission spectroscopy, which is a standard tool, and it's extremely powerful in this business, you will be able to identify these types of like unconventional crossing, topological crossing points. And indeed, so there are two papers back to back in 2019 carried out cobalt silicon, right? This were, they were reporting ARPIS measurements. Actually, part of the trick to do these measurements was very skillful preparation of the samples, because the cobalt silicon, even though it can be prepared very nicely as a bulk sample, right, it's very difficult to get a really nice surface. So they sputtered surfaces basically and onto single crystals, and then annealed them very carefully to have the appropriate quality for ARPIS measurements. And oh gosh, so this is just a summary basically of these data for different directions, different projections, and you can sort of see in the intensity profiles here that they make out these types of like Fermi arcs connecting the topological charges between the gamma point and the R point. And based on that, they thought that basically the story is finished, right? They know where the higher fold charges at the gamma point come from, right? And they're connected with the R point. It turns out actually the story is not quite as simple as that. Right. So these studies also showed that these Fermi arcs basically have a chirality, and this chirality in fact depends also on the chirality of the crystal. So these are different cuts here, electronic structure, right? At different energies. Okay, now there were also some quantum oscillatory studies, and I will return to these later on. So this is in a sense like a more conventional way of looking at the Fermi surface of cobalt silicon. So you have like a small Fermi surface pocket at a gamma point, and then you have the Fermi surface pockets at the R point. And we're particularly interested in these Fermi surface pockets at the R point. They are shown here, right? So depending on whether you believe spin-orbit coupling is important or not important, you have either 2 or 4 of them. These are typical data that were recorded and reported in these studies. And again, I will return to this later on. Of course, since the spin-orbit coupling in cobalt silicon is very weak, there was last year a very nice paper reporting ARPES in palladium gallium, where the spin-orbit coupling is much, much stronger. And they, on top of it, showed that since the crystal structure is chiral, right, if you have the other enantiomorph, right, enantiomer, right, the chirality of these crossings would change. Right? So that was part of the story that basically could now better resolve this higher fold crossing at the gamma point on the one hand, and on the other hand, they could see the chirality, or demonstrate that you can switch the winding by going to the other chirality. This is, of course, a kind of switching that you don't do with like a switch, but you just have to take the other crystal. But nonetheless, there's a certain element of control. Okay, now there's one thing missing in these considerations, and that is something that's been in the literature actually also for quite a long time. And I think I'm missing to cite some of the important papers here, so I apologize. This cobalt silicon belongs to a space group, which is space group 198. And as I mentioned in the beginning, the combination of this screw rotation, this non-isomorphic crystal structure with time reversal symmetry basically means that you connect basically by these operations, right, points, and you get degeneracies, you get a Kramers degeneracy, right? So that is something which applies to an entire plane, right? So you have these nodal planes, right? You have by crystal structure, you have a mechanism which enforces degeneracies of bands, right? In fact, this applies not just to electronic band structures, but also to phonons or potentially magnons, right? Since these nodal planes were not, they were mentioned but not fully appreciated, right, in this early work, or this works in the last year and a half, 2 years in cobalt silicon, one of the important questions is, well, what's their importance, right? And do they carry a topological charge? And they do, right? And where does this topological charge actually show up? And it turns out that actually, besides this fourfold crossing point, if you take it to set up a generic tight binding model, right, for this type of space group, you have these nodal planes, right? Nodal planes where they basically cut through the Fermi surface, these topological crossing points, and the nodal planes receive their charge from a wild point at the zone center. It's just a little bit energetically removed from the fourfold crossing, but you have to take the full picture, right, in order to, you have to do the full sum in order to get the full picture, right? Just a few weeks ago, a paper was published also reporting ARPES studies, and these guys also pointed out there's a single wild point in the zone center, and it receives its charge from these nodal planes. This is in platinum gallium. Again, same space group, larger spin-orbit coupling, right? So this was motivated basically by this search for this to satisfy this fermion doubling theorem. This is also known as the Nielsen-Ninomiya theorem. I apologize if I pronounce the name incorrectly. So band sticking in non-isomorphic crystals has actually been in the literature for quite a while. So this is some early study here. So in hexagonally closed packed systems, it was pointed out that you get this type of band sticking, and there was a set of materials also advertised where this could happen. Also, my understanding is that topological charges were not fully analyzed in these early studies. One of the things I found very interesting is that you can also study topological properties in a completely different setting. You can basically generate or build an acoustic crystal, right? And the way they do this is, take a look at this, is 10 centimeters. This is a piece of plastic, and they drill holes in it, right? And then they basically have like a loudspeaker, right? And they basically look how like acoustic waves basically travel, and then you can generate, you can design a band structure, right? So they did this, and basically this is the types of tubing that goes through this plastic block, right? And then they basically studied a crystal structure that looks a little bit like this hexagonally type of crystal structure. And for these band structures, you have these vowel points, and you also have these nodal planes, right? And then if you map out the acoustic waves, right, you find, okay, yes, indeed, these types of nodal surfaces exist, right, and they can be designed this way. But at this point, I mean, this is obviously like a classical system, right? And the question is, how important is it really for the electronic structure? Okay, so that was my unpolished introduction. Right. What I want to do now is tell you in a few slides what is important about the method that we use to study this. Right. Then I want to move on and show you some of our results. And the method that we use is quantum oscillations. And the way I would like to motivate this, obviously ARPIS is very nice and powerful, but you look at the surface of the crystals, you have a certain dependence on the surface quality. And you'd like to see basically the properties with much higher resolution at the Fermi level. Right? And the starting point here is really think of cathode resonance. Right? So you take a cathode ray tube, right? You have a Helmholtz pair of coils. This is just a big glass tube. You know this from your first semester physics, right? And then you apply a magnetic field, and the electrons basically experience a Lorentz force, and there is some ionization. You can see this nice beam. And you get basically just this orbit in which these electrons whiz around, right? If you apply in addition an electric field, right, then you basically get this spiraling effect. When we apply a magnetic field to a metal, we have exactly the same thing happening, right? However, the situation is of course more subtle, right? And we use typically a semi-classical description, right? And then we get, because the electrons are live in the quantum world, right? We get, when we apply a finite field, quantization basically of the states they can assume, right? So we have Landau quantization, and the Landau quantization, this is now basically just for a free electron system with a spherical Fermi surface, right? And then we get, as a consequence of this, quantization effects in the density of states. And these quantization effects in the density of states can be used to map out the cross-section of the Fermi surface on which the electrons basically undergo their cyclotron motion, right? And further properties. So here's a very basic example for the Fermi surface of gold. Right, when you apply a field along the 1-1-1 direction, you have two extremal orbits, right, around which the electrons whiz, and you get a beading pattern. Then in magnetization, right, as a function of magnetic field, right, of these two contributions. So these are the quantum oscillations in the magnetization that has von Alphen effect, but any quantity that depends on the density of states will show these types of oscillations. And now you can basically rotate the crystal, right? You can map out changes of the cross-section, and you can just sort of see if new orbits pop up. There's some key information that can be extracted from quantum oscillations, right? So, of course, on the one hand, you have like trajectories, right, in reciprocal space, but they translate basically into trajectories in real space. And you can get information on the effective mass of the charge carriers that are basically contributing to these quantum oscillations. One of the important things to take away is that the oscillations, which basically, whenever you change the number of Landau levels by changing the magnetic field, vary with their cross-section goes basically, their frequency goes with 1 over the magnetic field, right? And their cross-section is basically proportional to the frequency. So when we map this out, this is not evident from this plot here, but what you have to do is you have to plot your quantity basically as a function of 1 over b, and then you do basically Fourier analysis of the different contributions you've got there. Moreover, right, since you have a Fermi distribution, you will be sensitive only at the Fermi surface, right? And there are effects of finite temperature And so you can see the effective masses. This goes by the formalism of Lifshitz and Kosevic. Right, and so if you have small effective masses, you can do your measurements. You can see these oscillations up to very high temperatures. But if you're interested in highly correlated systems with large effective masses, you may have to go to very low temperatures because the amplitude of your oscillations drops off very quickly. So just for an amplitude for 50 electron masses, right, you would have to do your measurements well below 0.1 Kelvin. So this is the bit now which is important for the arguments why we think we see these nodal planes in our studies, and that's called magnetic breakdown. Right. So if you think of the free electron orbits, right, and they're whizzing around like this, right, in a lattice structure, there will be a band gap developing, and you get effectively then a so-called open orbit, right, and these small closed orbits. But when you increase the magnetic field, right, you force the system to undergo a tunneling here, right, and you can have a breakdown, right, and you can basically go back and also see these full orbits. This probability for having this breakdown basically can be written as like a function of the distance between these orbits and also of the radius of these orbits. So this is basically the distance, and this is the radius of these orbits, whether you have this tunneling. Okay, so this has been seen and studied to death. This is an example here from John Singleton's textbook. Where going to very low temperatures and going up to large fields, if I would zoom in here, you would see that there's additional small oscillations popping up. And these are the breakdown orbits basically happening, going around this way. So now on to our experimental studies, right? And actually, historically, the order in which things happen was that, of course, we worked on MNSI for a really long time. But then when we realized that these nodal planes played a very important role, we went back and had a look at cobalt silicon and realized that they're very important there too, but it's easier to tell the story the other way around. So what I want to do is to show you how these nodal planes, right, now affect the quantum oscillations for this Fermi surface pocket here, and that provides a very strong piece of evidence that these nodal planes actually exist exactly the way, because they're based on just symmetry arguments. Okay, and so what Andreas Schnieder and Kirill Alpin in particular and Moritz Hirschmann did was full analysis with different methods of the band structure, and they calculated all of the crossings, right? So this is the band structure of cobalt silicon. Here I'm showing the picture already where we take spin orbit coupling into account, which is quite weak. It's about 10 to 50 milli-electron volts at these locations. And then the nodal planes, right, which correspond with the brilliance on boundaries, are shown here in light blue shading. And then you get these different crossings all over the place. So they basically categorized them, looked at the windings with different methods, calculated the Berry curvatures and so forth, and mapped them out for these different bands. Right? So you can see that there is basically these degeneracies on the nodal planes. You can always see these bands going together, and then you have these crossing points in these different locations. They also studied this with a generic type binding model in order to confirm. I take on one hand doing this without spin orbit coupling, on the other hand with spin orbit coupling, in order to confirm the findings and also their classification of these topological charges. And now, this is an illustration now. And I'm sorry that the quality, this was in the last minute transfer now to my iPad, that the quality suffered somewhat of these pictures. But again, this is the band structure now without spin orbit coupling and with the different crossings marked, right? And we're interested here in these multifold fermions at the zone center and where they receive their charge from with respect to all of these other crossings. One of the things you can see is that basically the crossing at the gamma point, right, here receives its charges. So the way you do analyze this, this is also summarized in this table here. Right, is you assume band fittings up to a certain band, and then you can check what kinds of like symmetry enforced or accidental crossings are there, right? And then you have to do your sum, taking into account also the multiplicity of these points, taking different positions in the tree and so on. You find it always ends up to 0, right? So you're good, right? And so here, right, you find that basically the nodal planes provide the charge for this gamma point, right, without spin-orbit coupling. If you take spin-orbit coupling into account, the situation becomes more complicated, right? So you have charge at the gamma center, the gamma point, but then you also have charges close to the R point and the M point, right? And including then the charges of this is now considering and filling up to band 5, right? You find that actually there's a network of topological charges and they're all connected up. What do the experiments say? So now I'm basically back on safe territory. The experiment here is that these were measurements of the Shubnikov-de Haas effect. Shubnikov-de Haas effect is essentially the resistivity or the Hall effect. We measured both, right? So Nico did these measurements as a function of field. So you see dominantly, first of all, like the resistivity increasing, but then when you zoom in, you see that there are some wiggles on there, right? So you subtract something from the kind of background, right? And then you plot it as a function of 1 over b, and you find, there are these oscillations. And you do a Fourier transform of these oscillations, and you confirm, essentially, we confirmed, okay, what these 3 Chinese papers published was perfectly all right. Right? And actually, the assignment of these oscillations, just by seeing an oscillation, you don't know exactly which Fermi surface pocket this is. Right, you could, in principle, also have something that originates from the gamma point, but there's some arguments that basically say, okay, these two here are have to be attributed to the R point. So you see these 2 oscillations, right? And you think, okay, there are 2 Fermi surface pockets, and that's it. And without spin-orbit coupling, you have 2 sheets, and with spin-orbit coupling, you have 4. Right, so you think, okay, well, 2, right, perhaps spin-orbit coupling is not very important, right? We saw even like higher harmonics, and then you can measure the effective masses. This is the Slivshin-Pusevich behavior. And then finally, Nico very carefully mapped out the variations. He was changing the orientation of the field, so this dispersion is very flat, right? And now one has to do a little bit more careful assessment and basically do a calculation. So, I mean, as I said, like Mark Wilde masterminded all of this, and he's also set up all of the capabilities to doing these DFT calculations and calculating these Fermi surfaces. He's doing this with different methods. So before I get to these results, just a very quick note that we think that in our study, the samples, there is no broadening of these FFTs as an intrinsic broadening. That was one of the arguments raised in the earlier studies, that the spin-orbit coupling might be hiding underneath it very small. Right? So I'm going to just skip that. Okay, now, what 2 is just basically look at the orbits around this R point. Right? We say, okay, there are 2 Fermi surfaces. We assume we have no spin-orbit coupling, no nodal planes, and we calculate what kind of orbits we will get. Right? And then we take into account properly the effects of this magnetic breakdown. This will become important in a second. And since the quantum oscillations will show you the largest and the extreme orbits, the largest and the smallest orbits, if you orient the field along the 100 direction, right, it turns out actually they are roughly the same size. It turns out that actually they intersect. Right. So, but here they are essentially the same size. So you have dominantly 1 frequency, right? And not the 2. The black is basically our experimental data, and the red and the blue curves here are the theoretical calculation with Spain. And now, if you tilt it further away and you go towards the 110 direction, right, what you expect is actually if there are no spin-orbit coupling and no nodal planes, right, you expect 2 extreme orbits, right? 1 small, 1 large, and accordingly you expect basically dispersive behavior of the oscillation frequencies. And that's not observed experimentally, right? So you could say, okay, well, let's switch on the nodal planes. And now there's something which I should have mentioned, emphasized early on. One of the important things at the nodal planes is that basically the wave functions going, the quantum mechanical wave functions going through these nodal planes, they are orthogonal. So the nodal planes enforce a crossing, and that's a result of the topological properties of these nodal planes. And there's a consequence now for these Fermi surface orbits that the electrons or the charge carriers undergo, right? In a sense, what they do is that they switch, they don't stay on the inner circuit, right, or on the outer circuit, but because the wave functions are orthogonal at the crossing points, they will basically swap over to the other orbit, right? So we're basically showing this here, that we take basically this corner here, will connect with this part of the Fermi surface. So wherever they intersect, the electrons basically have to go onto the other side. And that's a direct consequence of the topology. But if you have no spin-orbit coupling, it turns out that basically you end up, right, with equally sized orbits, and you expect just a single frequency that's fairly dispersionless. But we observe two frequencies. Now you could go one step further and you say, well, let's switch spin-orbit coupling on, right? But presume we have no nodal planes. So this business with like the wave functions being orthogonal doesn't apply in our case, right? It's something we've just done recently, so let's forget about this. Let's do the conventional thing. When we switch spin-orbit coupling on, we get 4 Fermi surface sheets around the R point, right? And as we're like aligning the field along the 1 direction, these are nicely separated, so we expect 2 frequencies, right? But they're close by, and so we expect some breakdown, right? So we expect additional frequencies because there is some possibility, some kind of probability for the electrons to tunnel from one orbit to the other, right? This is shown here in the center, right? There's a certain weight, right? But you expect a lot of intensity, basically somewhat distributed between the two. And as you're tilting the field over to the 1-1-0 direction, right, there will be a more complex situation, right? You have basically these dispersive branches that you expect, right, and a lot of breakdown in between. But what we observe experimentally are just 2 dispersionless frequencies. And I guess now you're not surprised when I tell you that basically with spin-orbit coupling and with nodal planes, right, it turns out that the predicted frequencies we expect are in very good agreement with experiment. So this is a direct piece of evidence that these nodal planes play an important role, right? And then a consequence of that is, of course, that now you know you have to do your assessment of your topological charges across the brilliant zone correctly, right? And that actually the situation is more complicated than just having these higher fold fermions somewhere at the gamma point, which have been advertised mostly in the studies published so far. This brings me to MSI. And the point here is now, as I told you, right, these nodal planes are enforced by this combination of screw rotation plus time reversal symmetry. And if you have spontaneous magnetic order, you can ask what happens with the nodal planes. And again, I apologize for the poor quality of these figures here. What happened at the beginning of the presentation was that actually the keynote I didn't have a pointer on the keynote, right? So then we transferred it into PDF, and then the copy was lousy. But so the story is basically the nodal planes are shown in pink shading. The magnetization is shown in blue. The magnetization follows an applied magnetic field. So I apply the field in this way. I have basically spin split from the surface. I have the nodal planes around here. I have no nodal planes on the front and the back surface. Right? And if I rotate the field, then I basically destroy the nodal plane on this side, and there's no nodal plane here, right? And so forth. So there's a movie, right, where this thing is propelling, and you can see them switching on and off. And that's basically a nice element of control that we have now with these nodal planes as compared with like previous topological systems. Okay, I'm gonna have to speed up a little bit, not much, but a little bit. Very brief introduction to MNSI. It's a very, very long history. It was studied in the 80s as a weak itinerant ferromagnet. That's not really ferromagnetic, but it's ferromagnetic enough. Right? So there was a lot of interest in the ordering. So at 30 Kelvin, right, it undergoes a phase transition from a paramagnet to a Hale magnet, but it's Hale magnetic modulation, it's a long wavelength. When you apply a small field, you get a special ferromagnet. And these studies basically extended Stoner theory and basically introduced the effects of spin fluctuations, and then the Lonzo and Louis Tafer first to be able to calculate the transition temperature correctly out of measurements of the spin fluctuation spectra observed in inelastic neutron spectra. And at the time, there were also like quantum oscillatory studies done, and since I was in Gil's group at the time, and he told me when he saw these the Haas-van Alphen spectra, right? I showed you just like 2 oscillations for cobalt silicon, very controlled, is that this is the end of the civilized world, right? Nobody will ever understand this. We need a new understanding of the metallic state. So he was interested at the time in basically designing or coming up with an explanation for addressing clouds of quasar particles, and he was able to connect the spin fluctuations with the dressing clouds of these quasar particles. Right? I will show you in a minute how this works, but basically the idea is that you have a full account of the enhancement of the Sommerfeld coefficient of the specific heat. Right? On the one hand, through the quasar particle spectrum, you see in the quantum oscillations, and on the other hand, what you see in terms of like neutron scattering measuring these spin fluctuations. So this is the one slide alluding to the skyrmions. So MNSI, when it orders at 30 Kelvin, of course, this displays this complex magnetic state, which develops this magnetic modulation. And when you apply a small field, you get the skyrmion phase, which is shown here, right, in a small phase pocket. So this is a completely different line of work. One of the things that came out of this work is that you see an additional contribution to the Hall effect in the skyrmion lattice phase. This is something we call the topological Hall effect. When you do transport measurements, you want to connect or have an explanation, ab initio explanation for this Hall effect that you see, or these fancy phenomena. So we did some studies where we measured Hall effect in a series of manganese, iron, silicon. And Frank Freimuth and Yuri Mokusov and Stefan Blügel did calculations, DFT calculations using FLIR, of the anomalous Hall conductivity and the barrier curvatures and this topological Hall signal. Right. So I'm going to just skip this slide here. And with this slide, I just want to show you, without going into the details, that actually there's excellent agreement between experiment and theory of this anomalous Hall contribution and this topological Hall contribution. And that already showed us that DFT calculations give a lot of valid information about the Fermi surface, and that actually, in a nutshell, one can think of like the spin split state as just like, even though it's complicated, as just like a rigidly spin split state. Okay, so this brings me back now to this business with the nodal planes and these non-symmetric symmetries. And that was considered so far for space group 198. This is where I started for the cobalt silicon, and with this very early work in 2017, and very early work. But now, as I mentioned already a couple of times, when we apply a magnetic field, right, we can sort of break reversal symmetry. And then we have to consider these other magnetic space groups. And there's something that Andreas and in particular Moritz and Pierre, but Moritz, I think, was the main guy here, did very carefully. Right? So they looked into the electronic properties and the topological properties in particular of the electronic structure when you apply a magnetic field in the field polarized phase. So I have nothing to say about the skyrmion phase here. Right? It's just for the field polarized phase. Here's a picture of the calculated ferromagnetic band structure in MSI, and you get a very similar situation to the cobalt silicon. However, you have more bands, right? And then if you do this whole thing, basically spin split, taking into account spin-orbit coupling. So this is just for generic model. You can see the nodal plane and these crossing points here. Right. You see that there are more crossings, right? But the story essentially stays the same. Right? So you have these Wahl points, fourfold crossings, and then you have these topological protectorates wherever the nodal plane or the Fermi surface hits the nodal plane. Okay, now all hell breaks loose, right? So Mark and some of the students, they measured the Haas-van Alphen effect in MSI. And you don't get just like 2 frequencies or 3 or 4, right? But you get a nice and even 40, right? So these are the spectra. These are measurements that go down to 35 millikelvin. So these are the oscillation frequencies, right? They show strong temperature dependence because they have different effective masses. And if you change the orientation of the field, you can map out. This is a rotated plot. And again, I apologize for the poor quality. As I said, like last minute before I started the presentation, you can see that some of them are highly dispersive, some are not dispersive, right? And now one has to be, this is really a very, very difficult job to do the proper assignment, right? And all of this is, you can find in this paper that was just recently published. So I'm not going to go into the details there. There are a few frequencies which are the really interesting ones. So for doing that, here's a list of all the frequencies, right? And they can be fully assigned to these types of, we have 10 sheets of the Fermi surface. And once you sort of like go through this, you find that there are some sheets which are centered on the gamma point, right? There are some sheets which are centered on the R point, so you can sort them out. And then you have some sheets which are centered on the gamma point, which basically hit the Brillouin zone, and so they cut through the nodal planes. And these are the ones that we want to focus on. So the assignment has been fully done, right? You can tell for these 10 sheets whether they're electron and hole pockets, right? And what kinds of like character they have. And here's actually now a list also looking into the density of states and the contributions due to the specific heat. We can compare this with the effective masses that we get out of the temperature dependence of the oscillation amplitude. And it turns out actually that the sums add up. So we see all of the Fermi surface sheets there. Everything matches very nicely. This is basically also the origin of saying the quasi-particle quasi-particles in this type of Landau Fermi spin polarized Landau Fermi liquid are dressed with like strong spin fluctuations. So all of this is consistent. Here's now the main argument where we see that the nodal planes play a very important role, and that in the direction of the magnetic field, right, the nodal planes no longer exist. And the argument goes exactly the same way I showed you for the cobalt silicon, right? It's just that you have to pick out the right orbits. And so this is this complicated Fermi surface. And now when we apply the magnetic field, so this is rotated a little bit, and I'm showing you a different cut here, right? So actually this part here is somewhere here, right? But it's rotated a little bit. And let's suppose we apply the field along a 0, 1, 0 direction. And then we have two dominant frequencies in a particular part of the spectrum that we can very clearly assign, right? Where one of them is basically cutting across the nodal planes, right? It's not in plane with the nodal plane, but it's cutting across the nodal planes. And the other one is basically on the face where the nodal plane has been suppressed because the ferromagnetic moment is pointing in this direction. And this is summarized in these plots here. This is basically the section here, right? So we get 4 orbits, those intersecting orbits, right? And again, there's no magnetic breakdown, right? You have to cut across onto the different segments, so to say. And when you calculate this, you find that there is one frequency, even though you have 4 orbits contributing, right? And it shows a certain dispersion that's also in agreement with the experiment. Whereas if you would have no nodal planes, you would expect frequencies up here and down there. So this is not observed. Sorry. On the other hand, in the direction where the nodal plane is suppressed, we have we would expect actually, if there would be a nodal plane, right, that the separation of these orbits, because you see the maximum, the extremal orbits, right, it would be a little bit to the before and to the back of the nodal plane, but the symmetry would be the same, right? But what we observe is actually something where we have two different frequencies, right? And again, this is in agreement with calculations. So we see two frequencies here, right, instead of one. And that is an indication that the nodal plane has been suppressed. I'm really running out of time, so I don't know whether I'm sad to say that I have to skip the theory slides. Of course, Andreas and they did these calculations of these eigenvalues, right, to see that basically how the orbits connect. They also calculated the Berry curvatures at the Fermi surface, right? And we see that a lot of the Berry curvature is basically pinned to the Fermi surface, exactly where the nodal planes cut. And finally, it turns out that actually you can even see, you expect Fermi arcs, right, due to these nodal planes when you apply a field and suppress them in a certain direction. This is not the case. I showed one example for cobalt silicon when you have them on all three faces. Last slide. This is a big table just to impress you all. So Andreas and Moritz and Carol, they did a complete assessment of all magnetic space groups and looked where these topological nodal symmetry and forced topological nodal planes are to be expected. Right, so it's all marked in here. It's all where the little t's are. Right. And there are more materials where they suggest that this should actually play a very important role. That's why I want to stop. Thanks very much. I'm happy to take questions, and thank you for your patience.
Okay, thank you very, very much. Now let's see, we have some questions maybe from the audience. Please raise your hand and I'll give you the microphone that allow you to talk or promote, in this case, to panelists maybe. Niels, I think you're going to be switched now to panelists, and you should be able to. So Niels, go ahead and unmute yourself and ask your question maybe.
All right. Hey, Christian, thanks very much for this very nice talk. I was wondering about essentially the comparison now between manganese silicide and cobalt silicide. So what you said in the beginning is that for the manganese silicide, you would expect to have some sort of Fermi arcs between these nodal planes and some other wire points, but that they are not there in the case of the cobalt silicide. Could you elaborate a little bit more on that, why that's the case?
Because so if you have, okay, this is, as I said, like I'm not very, this is the first time I talk about these things, so probably I'm going to screw this up really badly. But the point is the following, right? You're not going to get a gap that allows you to do a cut such that you can see the Fermi arcs connecting basically the charges in the zone center to the nodal planes, because you have the nodal planes on all three sides for the cobalt silicon. For the MNSI, you suppress the nodal planes due to the ferromagnetic magnetization, right, in one direction, and because of that, you expect Fermi arcs.
I see. Okay.
I'm not sure whether you're satisfied with this answer, but
that's what he's going for.
No, but I think it's very close to the truth. So I have to put it this way. And if you really want to know the details, you go and ask Andreas and these guys.
So essentially, the argument is you cannot define this two-dimensional quantum Hall slice.
Yes.
Because all of your
because it's three-dimensional.
Yeah, because all of the four planes are not gapped. Okay. Yeah.
Right. You can see it a little bit here in this picture, right? The cobalt silicon is what we did in this light blue shading, right? It's like on all three sides. And because of that, you cannot basically define a cut that shows you these Fermi arcs.
Yeah, yeah.
But you know, you can ask, well, you do see Fermi arcs in the cobalt silicon experiments, what's going on there, right? And there's no problem with that, because this is basically a flow of Berry curvature, not between the nodal planes and some charges. It's just that basically, I guess, it wasn't realized that close to the 4-fold points, there's another 2-fold point, and that is connected with the nodal planes. And that's what was published recently, I guess, in the Nature Communications paper.
Okay. Gisela, maybe you can ask a question now. Yeah, we can hear you.
Thanks for this nice talk, Christian. I have a question from the experimental side. You mentioned it somehow in your talk, but what is the requirements for the sample quality? Because if you need to have a perfect band structure to explain your data, and therefore you need, I think, perfect or very large crystals.
Okay, so this is there. I mentioned that the crystal quality in two locations of the talk, right? The first one is the requirements for the ARPIS studies, and the problem with the cobalt silicon in MNSI is because it's cubic, it doesn't cleave, and so my understanding is because of that, there's difficulties in getting the surface in a way that allows to do ARPIS measurements. Cobalt silicon and MNSI as such grow very nicely metallurgically. So it is possible to grow sufficiently clean bulk samples, and for the quantum oscillatory studies, you need bulk samples. Okay? And then it's in a way also nice because you can really sort of like probe the bulk level in the surface and then backtrack what's going on the surface. This is, I know that there's a history of like debate between which is better, ARPIS and quantum oscillations, and I don't want to get into this territory. But then I also mentioned the sample quality in terms of studies that were published by these Chinese colleagues. And they saw a little broadening in their asymmetry in their Fourier transforms, right? And we have samples which also show the same thing, but they're lower quality in terms of the resistance ratio, right? So in terms of preparing these materials, it is all right, but it's usually the way you can do quantum oscillations on materials that love to grow by themselves. And that's the case here, right? And if they don't like to grow, right, it's difficult.
Okay, thank you.
Daniel, I think you're next. If you would like to unmute yourself and ask your question. Thank you.
I have a rather general question, actually. Your main problem was to check whether some of topological features are protected by particular symmetries. Fine, you find many cases, and which indeed, actually, if you keep the symmetry, then these crossing points in band structure, for example, are really protected. But the point is that it's very rarely checked, and I don't know whether it's really a problem for you, but in general, whether this particular symmetry may be spontaneously broken, whether it is really protection will survive, for example, some interaction. For example, you consider in the very beginning, like a line of Dirac nodes when we have two paraboloid kind of crossing. When you have a line of which looks like line of Dirac nodes, which may be protected by particular symmetry, but that's typical situation for what we call excitonic insulator. As soon as you include electron interaction with electrons in one band and holes with the other band, then you open the gap and you remove this protection. You reduce symmetry and remove this protection. Is it problem for some of your things?
Well, I mean, it's on a
whether they may be spontaneously the symmetry which protect your crossing, whether it's stable with respect to symmetry breaking, of spontaneous symmetry breaking.
Well, okay, so I could let's put this. Well, first of all, in order to have these topological protectorates the way I advertise them, you have to have the Fermi surface crossing the nodal plane. So any type of interaction or correlation effect that will somehow restructure your Fermi surface such that it no longer crosses this nodal plane will be detrimental to this thing, okay?
Yeah.
It's just that, so the argument, it would be better not to call it like a hardcore protectorate, but to say it's insensitive to the details, because in our case, the Fermi surfaces are so large that it will somehow extend across the Bremensson boundary, no matter what, right? It's nonetheless, right? So that level, it is not a problem for us, right? Because I think we're in a regime where we're much less sensitive to these types of effects. it is nonetheless, if you have a symmetry breaking, right, and the spontaneous ferromagnetic order is a type of symmetry breaking, it does suppress them. It lifts the symmetry, so it basically goes against the symmetries that establish nodal planes. So these two effects, I would base this is how I would basically position these results. Let's say, and in a way, it's not just a disadvantage, but having the symmetry breaking, you can control, right, what is happening with your protectorate, right? So anyway, I guess that's all I have to say about this.
But in principle, it might be even very useful. For example, if your topological feature depend on particular symmetry, just by slightly breaking the symmetry, for example, by applying uniaxial stress or whatever, you remove some of the symmetry elements, and you may kind of control and modify somehow just these topological features.
Well, so that,
but,
okay, so there,
the dangerous point is whether these things occur spontaneously, because you rely completely on particular symmetry, and whether it's stable,
but it would have,
whether the symmetry is stable, this question.
Yeah, so as I said, like the symmetry breaking that we have in terms of the spontaneous ferromagnetism or magnetism basically kills this effect, but it is something we control with the magnetic field.
No, but it may be, for example, spontaneous change of lattice structure, some spontaneous distortion, which would remove, for example, some of the glide planes or whatever.
Yes, I completely agree. On the other hand, on the wish list I showed in the beginning, I said, well, you want to have, for one, you want to have them really far separated, and in this case, you get them as far separated as possible, so you expect a large response. On the other hand, you might worry about topologically trivial bands, short-circuiting your effects, and this is something you can see in this picture here. Even the tiny pockets up there, right? This is something we know from the calculations. This is difficult to prove experimentally, but we expect that they also have these topological protectorates as long as they basically extend over the brilliance on boundary. So you will not get short-circuited by trivial bands when you have such a generic mechanism.
Okay, very good. Thank you.
Pavlo, let's go next to you. If you don't mind unmuting yourself and asking a question. Thank you.
Thank you. So my question is also related to Fermi arcs. So what is the role of the Fermi arcs as a quantum oscillations? In particular, it is known that in conventional violent Dirac metals, it is possible to have a closed bulk surface orbits where electrons travel through the surface and through the bulk and then again through the surface. Thus, there will be additional frequency. But what about this material? Is there an interplay between these long helical Fermi arcs and nodal planes?
Yeah. Okay. So in the studies that we do, we study basically macroscopic samples. So I don't think that anything like this will be relevant here. There is work by Philip Moll and others where they study these microstructured samples. And my understanding is that they basically see some kind of combination, at least that's how they interpret the data, some kind of combination between Fermi arcs and like some kind of trajectories through the bulk. I'm zero experience with this, so I cannot comment further. But it might be interesting in these materials, right, to study microstructured samples, to reduce them down and see what happens there. But you might also get other effects. The Fermi surfaces here, this is in a way one of the things to appreciate. The Fermi surfaces are as complicated as get, right? And and yet we have a simple feature. Isn't that cool? Right? But it may not be the right thing to look for through these types of studies, to look for these types of like effects. Okay. So it's, I'm sorry that I cannot give you more of an answer to that, right? But I would say in our studies, the Fermi arcs are not important. I find it very interesting to consider possible effects they induce in thin films or something like this, and I can control this with the field direction, for instance, or to look in cobalt silicon, for instance, in nanostructure, the microstructured samples, where you get some funny effect where the Fermi are involved, with symmetry breaking by strain, something like that.
Okay. Thank you.
Thank you. And then I think the last one from Tyler. Can you go ahead and unmute yourself and ask your question?
Sure. Hello. So two questions. So one, what is the topological invariant for these nodal surfaces? I kind of have a hard time picturing how to calculate the Chern number if the topological invariant is indeed a Chern number. And then the second question is, considering the bulk boundary correspondence, how do the Fermi arcs connect to the bulk projection if I look on the surface of the bulk projection of the nodal planes?
This is a question I don't feel qualified to answer. I will try and give my best, right? It is Chern numbers, right? And the Chern numbers, but you have to integrate, so to say, this is what I understand. You have to integrate over the entire brane zone and do this properly. And then you find out the topological invariant. You have only Chern numbers in these systems. But I'm repeating what I've learned from Andreas Schnieder, and if you want to know more about this, I would recommend that you just ask him directly. As concerns these Fermi arcs, how they connect, let me just go in here. I showed you this, oops, I'm sorry. Showed you these pictures here, right? And we did have some discussions how they basically connect between different points, and then decided in the end of the day, at least in the paper, not to make too much of a statement about this. What we know is that the Fermi arcs basically here connect the Wahl points to the topological nodal planes, and this is also something that, the Wahl point, the gamma point received their charges from the nodal planes, and my understanding is that the Fermi arcs we see here are part of that story, right? More than that, I'm afraid I just don't know.
Okay.
Sure. Okay, thanks.
Excellent. I believe that's the extent of all the questions that we've had, and I thank all the 145 of you that showed up today for the talk. And I think it was like 27 countries, so doing well still. And thank you, Christian, for the nice talk I'm preparing. I know it's tough. The first time you give any talk, it's pretty tough to put it all together. And that's been a lot of effort. I understand that. It's really not easy. Well, once it would be more polished later.
I apologize for all the things I left out, and I didn't mean to do any.
No, it's great. It's actually a wonderful review of as well of the strength of the signal oscillations tool, which has not been exploited as much lately. It was all this ARPAs and Bahoo, and then you have these fantastic.
Well, I think it's an interesting. Thanks very much. Much appreciated.
Sorry, you were saying that it was interesting?
No, I said I agree that in terms of the methodology, like the quantum oscillations really can make a very important contributions here.
Yeah, I think so. I think it's going to trigger a lot more exploration in that direction. So thanks again.
I also need to run. Thanks, Christian.
Everybody stay safe, get your vaccine, and we hope to see you next week.
Thanks very much.
Thank you.
Bye.
Enjoy the wine.